stormwater section. My name is Brian Simon. I'll be the moderator for this section. We've got some really great speakers here this morning. Thanks for everybody for making it out and getting through the ice and skating away here. I hope it wasn't too treacherous. Our first speaker this morning is Thompson. He is a PE at CFM in the Stormwater Community Practice Leader for MSA Professional Services. He's going to be talking about stormwater quality planning for municipalities. I'm going to turn it right over to him and we'll get started.
All right, thank you. This is working? Yes? Sounds like it. So yeah, I've got a presentation called Stormwater Quality Planning for Municipalities, and I'm gonna fess up right away and say that the evolution of this presentation started out to an audience of wastewater treatment plant operators, and a lot of treatment plants in the upper Midwest, certainly in Wisconsin and a little bit here in Iowa, are facing numerical standards for their effluent. And the need to put in large mechanical upgrades is causing them to look outside the plant at other non-point source applications where they can get similar phosphorus reductions and sort of find a more cost-effective application. And so about halfway through this presentation, the style is going to change a little bit, and I'm going to look at different urban BMPs in a planning setting to see where we might find phosphorus reductions in the way of implementing new BMPs. The other thing I'm going to fess up about is this presentation focuses a lot on water quality modeling. And for those of you that that work in the field, you understand the adage that all models are wrong, but some provide useful information. And with that, the model represents, in this case, water quality models in particular, represents a little bit of a gray box. I'm not going to call it a black box because you can sort of see into it, you know what's going on. But imagine that there's this huge field of research and all this data, and water quality data in particular lends itself to a certain amount of randomness. And so just imagine there's this graph with all these dots all over the place, and there's a line fit through it. Well, the model, of course, follows that line, so it sort of dumbs down a lot of scatter and a lot of variability and comes up with a single answer. And so a lot of the stuff I'm going to present today is going to be, wow, look at that awesome single answer. Just recognize that there's some scatter with it. And in the context of stormwater quality for municipalities, especially in that larger picture of looking for improvements relative to what's going on right now, that scatter becomes less important than the relative order of improvement. So maybe there's still some uncertainty about what the actual answer is, but you know that the ultimate result is better. All right, so just dive into it, maybe. There we go. So a BMP, this is something in practice that always makes me laugh. A BMP is a best management practice, and whatever it is you decide to do, it's the BMP, it's the best one. Well, how do we know? I mean, it could be a management practice, it might be an acceptable management practice, but it's not necessarily the best management practice. So the idea is, anyone with a little bit of education can come up with a list of good management practices, certainly things that are better than what's going on right now. But in the context of a municipality, you're spending taxpayer dollars and you want to try to find the best economical solution, so you got to figure out what is the best management practice. And of course, the way you go about doing that is through developing a water quality plan. Now, what we'd like to get to at the end of the day is a map that looks like the one on the right, and you can sort of imagine red is bad, so that must be a map of water quality and pollutant loads, and where it's red, there's a higher load. So hey, if we're going to spend our dollars, let's look in those locations. And then as we sort of dissect those locations and figure out what is specific to the land use, what's specific to the human traffic, and all that sort of stuff that's going on in that area, maybe there's a particular practice that not only is more efficient, but it's also more suitable to that location. Well, how do we get there? Well, this table of scope of work items kind of describes that. So we start out with preparing a water quality database, and I'm going to zoom through that pretty quick because for those of us that are in the field, it's pretty standard fare and pretty easy to understand for those people that really aren't in the field. Then we construct this water quality model, and again, that's really the bulk of what I'm going to talk about today in terms of conclusive evidence. We do this water quality BMP alternatives analysis. So we can look at street sweeping, catch basin cleaning, retrofits to existing facilities, and then of course the all-encompassing build something new. And again, the idea here is we're looking at municipalities who are looking to make things better. And so let's look at the existing system first, because you've got a lot of investment in infrastructure, and by making small tweaks for relatively low cost, you can get quite a bit of improvement. Then we do some designs and prioritize according to social acceptability and, of course, cost effectiveness. All right. So again, I mentioned we're going to kind of go through this pretty quick, but how do we develop this water quality database? Pretty standard fare. You start out with some nice mapping. So on the board, we've got a drainage network, and the red lines represent the sub-watersheds that go to it. So we're looking for the natural channels, the ditches and the swales, roadside drainage systems, storm pipes, and of course your BMPs, your management practices. So you subdivide all those things up into what's draining to what, and what's a critical resource, and what is it you're looking at. And of course, if there's a BMP, you want to delineate everything that's draining to that BMP, so you have an idea of what is the load going to that BMP and what's the demand that we're placing on it. Well, then you add a layer, and those of you who are familiar with GIS understand that there's all these different layers. You can kind of put them on top of each other like old style transparencies, and then as you sort of look down on them, you can see that there's all this different information that's confined to that geographic area. A lot of the models are concerned with runoff from impervious areas, which I'll get to in just a second, but also from the pervious areas, from the turf, from the vegetated areas, things like that. And the two principal ways of looking at that are either through the hydrologic soil groups as classified by the USDA, or by the soil texture, which also are classified similarly. You know, sand, silt, and clay, or HSGs A, B, C, D, which are more or less comparative. And so you get a map like this, same watershed background. And then finally we look at land use, which leads us to impervious areas. So the land uses you're looking at there are open space and low density residential, medium density, high density, industry, institutional, that type of very standard fare for urban planning. Where it really gets important is identifying the impervious area and the connectivity of that impervious area. So the connectivity just has to do with, you've got this roof or you've got this parking lot, this impervious area. What is its drainage characteristics relative to the stormwater collection system? Is it directly connected, or does it flow from the impervious area onto a length of pervious area and then into the collection system? And at what point does it become disconnected? There's a very, very significant difference in the runoff contributions as well as the pollutant transport from impervious area that's connected versus disconnected. So what I'm showing on the board here is a little study we did for a suburb of the city of Madison up in Wisconsin. And they didn't have a whole lot of information on their land use or on their impervious area. So we just took some samples and we said, hey, this neighborhood looks like it's got a different development pattern, and this neighborhood has a different development pattern. And the black polygons you see there are the different layers of imperviousness. Well, then you can apply various rules of thumb to say, all right, is this type of impervious area connected or is it not? And this is a whole bunch of text that I gathered from about a 5-minute internet search of impervious area connectivity. And I found references from Philadelphia, Wilmington, North Carolina, Washington, D.C., and New York, and the state of Wisconsin in particular have statewide standards for people who are doing stormwater quality assessments to determine what the level of connectivity is. And they all kind of boil down to the same thing, which I've sort of put on the board there as sort of the envelope of occurrences. And it's kind of interesting, you know, they're very specific because you got to be specific when you're doing calculations. But, you know, the first bullet says contributing flow path is no more than 75 feet. Well, darn it, I'm at 76 feet. I guess I'm now not disconnected. Well, really? I mean, there's that scatter that's involved, and there's factors affiliated with slope. And of course, there's construction practices. You know, a piece of pavement that's glass smooth will behave entirely different than a piece of pavement that's all cracked and broken and it's got a bunch of different elevations due to, you know, heaving and things like that. But these generally describe a fairly decent way to estimate the level of connectivity. Of course, if you don't want to go through that effort, the folks at the USGS, the Wisconsin DNR, and in part the city of Madison and the city of Wisconsin, again up in our city of Milwaukee up in Wisconsin, have done some exhaustive research. And this is a table you're not intended to even look at, really, because it's got too many numbers on it. Let me simplify it a little bit. Describes the level of connectivity of typical Midwest land uses. And the rows on the top are basically open space and residential. And that top number, 5%, 13%, 24%, that describes the typical amount of connectivity of residential land uses. And then on the bottom, we've got industrial, institutional, commercial way on the right side. And you can see those numbers are much, much higher. So the idea is the higher level of connected impervious, the higher the density of that connected impervious, really the worse it's going to be for the watershed. So this slide is something that I borrowed from the Center for Watershed Protection, and it provides kind of a nice sort of visual image of what does this connectivity mean. So the connectivity is not only producing a lot more runoff, because impervious area obviously sheds the water rather than absorbing it, but it also distributes it faster because the whole idea is get it out of town. We don't want it flooding. We don't want it causing a nuisance for us. And it changes the physical characteristics of the flow in these streams. So on the left, you've got a relatively low impervious area, probably approximating kind of a natural condition or very, very low density rural type development. And on the far right, we're getting up there into the 20%. And they show that normally right around the 10% mark is where we start seeing impairment to the streams, at least as far as they're measured physically. Well, we see the same thing when it comes to looking at water quality loads. So these charts here, I got a laser pointer, I think. Yeah. The blue line shows total suspended solids loads as a function of directly connected impervious area, and the red line shows total phosphorus. And I'm really going to focus on phosphorus because it's a smaller number, it's a little easier to wrap your mind around. And what we're seeing here is the directly connected impervious area increasing from 0 to 100, and then these are just the loads in phosphorus and loads in sediment, and the loads in phosphorus. And these little dots are the different standard land uses from that previous file. And again, this is all model data, so imagine there's some scatter around there. But basically, the thing to take away is for a typical Midwest community, with a mix of land uses and silty soils, which hydrologic group B soils, you end up with about 260 pounds of sediment per acre per year of development, which is a lot. And you end up with about a pound of phosphorus per acre per year. So just remember a pound, because the slides as I go on are going to kind of reference back to that 1 pound per acre per year. This slide is, first of all, I noticed right away when I was kind of doing my review this morning, the units are pounds per acre per year, not pounds per year. But this shows where the phosphorus is coming from in terms of the connected impervious area. So we got commercial land use, industrial and residential, and an average out, just looking strictly at the connected impervious area within whatever type of land use we're dealing with, about 1.2, 1.4, and 2.4 pounds per acre per year. And it's kind of interesting that the residential has higher numbers than the commercial. And there's some speculation about that. I think the folks at the USGS in particular are doing some research on it, have identified that it's not just the connectivity, but it's also the size of the piece of connected impervious. If you think about a residential lot, the building itself is smaller than a commercial building. It's smaller than an institutional building. And even though it's connected, it's got a lot more perimeter around it. So the atmospheric load, the load from grass clippings, the load from leaf drop, things like that, are able to accumulate on it a lot more. As opposed to imagine a large commercial parking lot. There might be a lot of vegetation around the perimeter, but there's not as much in the middle. And so the sort of pervious areas are being affected not so much by the impervious itself, but by the ability to collect it and transport all of that organic matter and the things that go along with it. This is in comparison, of course, to the undeveloped and the landscape, which undeveloped is sort of, just basically historic, pre-settlement type conditions, as opposed to, it's being graded out. And landscaped is your typical yard. And the modeling is in particular not very good at undeveloped conditions, so take that with a little bit of a grain of salt. But the idea is it shows there's, a factor of 2, factor of 3, factor of 4 in terms of the overall loads coming from the different sources. And again, it's that impervious area's ability to deliver the pollutants, not so much its ability to generate them. All right, so crunch the numbers. All right, most of this stuff is done using GIS. In fact, all of it really is done using GIS. So if you kind of go back to the beginning of my presentation, you've got watersheds and drainage network, you've got land use, you've got soil, you've got impervious area. You have all of this data that gets crunched down. And so you might have one watershed that's got a designation of which BMP it drains to. And within that, there's subdivisions that are soil type A, B, C, D, or sand, silt, and clay. And you've got different land uses, and you've got different impervious areas, and you've got different connectivity. And you can imagine that one watershed might break down into hundreds, if not thousands, of individual unique combinations of all of these different source area parameters. Well, in GIS, it's really just about as easy as a push of a button to crunch all of that data. And when you crunch it all, of course, you can then import it into a model. I've been talking model. These are the two models that, in my experience, and I've been doing this now for over 20 years, that really get the most play in urban water quality planning. The first is the WinSlam model, the Windows Source Loading and Management Model, WinSlam. And that model is put out by this outfit called PV and Associates. It's really got its origins with the University of Alabama and a professor by the name of Robert Pitt. He's been doing a lot of research on small storm hydrology and urban water quality. And it used to be back in the day that this model P8, which I'm going to screw up, but it's like pollutant passes through pits, ponds, puddles, pools, something P, 8 Ps. P8 used to be, back in the day, the superior model in my opinion. It was much more able to do networking and evaluate complex systems of management practices. The SLAM model has eclipsed it, specifically in the last year, because it's also become able to model distinctive networks of different BMPs. But the WinSlam model in particular has gotten lots and lots more attention in terms of research on different practices, grass swales, permeable pavement, catch basin cleaning, all sorts of different things that the SLAM model can do that the P8 model cannot. And so WinSlam is really kind of taking the forefront in the way of doing these water quality assessments. And in fact, the data I'm showing you today is pretty much exclusively from the WinSlam model of different projects that we've worked on. All right. So again, you've got all this data, and you can crunch it down in GIS, and it's really, really pretty easy to do. And sort of case in point, this is a small little community. They had no real reason to do a water quality plan, but they just decided, hey, we live on Green Lake, which is a resort class lake, and we want to make sure we're doing what we can to protect the quality of that lake. So, hey, what can you guys do to help us out here? And we don't have any money to pay for it, by the way. So we did this study, and I think it took us about 20 hours, which is not very much. And we studied a community of about the size, I don't know, 3,000 people or so, and we were able to do these pollutant hotspot maps. So there's different colors you can see on the board there. The darker the color, again, similar to that first map I had in the introductory slide, the darker the color, the more the load. And so the community was able to say, oh, well, geez, you know, we have a storm sewer that runs through here. Maybe we should do something about how water gets to that storm sewer, or maybe we should put something at the end of that storm sewer to collect the loads. When we looked at all of these different loads across the board, and again, there's different land uses in there, there's different soil types. We had a study area of about 690 acres, or 714 acres on 690 pounds per year. So again, we're hovering right around that 1 pound per acre per year of phosphorus. All right. Now again, this is dovetailing in with this presentation I mentioned that was geared towards wastewater treatment plants. And my colleague who was presenting had a slide, of course, that said there is a lot of pee in poo. I had to follow that up by saying, well, there's a lot of pee in stormwater too. And this kind of shows, again, that conclusion that we're dealing with about 1 pound per acre per year of phosphorus load in your average urban land use. Now, obviously, the open space and park are lower than that, but some of them are higher, and they average out to about that 1 pound per acre. All right, so bearing in mind 1 pound per acre per year, and you've got this nifty hotspot map that says all these different locations have more or less loading, how do we go about figuring out what to do? Well, of course, it all is about targeting that management practice placement to figure out what is, in fact, the best management practice. So let's look at what they're already doing. Street sweeping, catch basins, roadside swales, green streets, detention ponds, biofilters, underground storage, all these different things that we can sort of factor into the structural and operational practices that control water quality in the community. All right, street sweeping. So again, the USGS, along with the City of Madison, just recently did a big study, and I'm not going to get too much into this for fear of sort of getting into the next presentation, because they're going to talk a lot about it, I'm sure. They looked at the efficiency of mechanical sweepers, like that Pelican variety on the right, and the Elgin variety on the, Pelican on my right as I look at it. The mechanical sweeper on the left, and the high efficiency vacuum sweeper on the right. And what they showed was that mechanical sweeper, given certain assumptions, you know, density of parking, type of street, and the number of frequencies that they pass each week, and I assumed once per week. It's a pretty aggressive street sweeping program. They get about a pound, 0.7 to 1.4 pounds, the averaging of about a pound per street mile per year removed by street sweeping, which is not bad. You switch over to a vacuum sweeper, though, much higher efficiencies, and you get between 2, 3, 4 times that amount. So just by changing the operation of a community to do a different type of practice, you can get a very, very large improvement. Similarly, changing when you sweep or having parking bans on the streets when you sweep can make a big difference as well. This is actually a photo from my own neighborhood. The photo on the right in particular is I think, really illustrative of what goes on here when you've got a sweeper. It has to pull away from the curb because there's a car in the way. And you can see right there in the corner, it's leaving all the leaves and things that have accumulated there because the brushes just simply, instead of bringing it into the hopper, are now pushing it out because there's nothing to brush up against. It's sort of like sweeping the floor without a dustpan. There's nowhere to collect it. Similarly, if you have a parking, I should say contrarily, if you have a parking ban, well then you don't have that issue. Or if you sweep residential streets during the day when people are mostly at work and sweep commercial late at night when businesses are closed, you can sort of have that same result. And here's that same table again, and it shows how when you have no controls versus with parking controls, you can get, almost double the efficiency of your street sweeper. All right. Catch basin cleaning. So you've got all these manholes in the street. You want to rebuild your street because you've got a capital improvement program to rebuild that street. Replace some of those catch basins with sumps. And this shows the efficiency of those catch basins as a function of the density and the phosphorus reduction. So when you've got a typical land use, low density residential, medium density industrial, getting up there in the higher intensities of directly connected impervious area, you can get 10%, 15% reductions in phosphorus that you would not have gotten otherwise. Basically, you're rebuilding that street anyways, put in some different practices and improve your water quality. Roadside swales. This is a photo of a city that's sort of known for clay. Its city is called Marshfield. It doesn't drain. It has clay soils, but they've got a lot of vegetated roadside swales. And everyone thought, well, we put those in because we don't have any slope, everything's flat, can't drain anything with a pipe, so we got to put in a swale. Well, they looked at, we actually went out and did some infiltration testing and did some actual clear measurements and found that with these different swale densities, we get really very efficient phosphorus reductions. In fact, when you get a swale density up there about 400 feet per acre, you get about 70% reduction of the phosphorus that's in the stormwater runoff. And here's that same kind of graphic. So if they're high density residential or medium density residential, you can get really substantial improvements through phosphorus reduction in swales. You can, of course, augment those swales by putting in engineered soils and putting in underdrains, and in even communities that are known for their clay can have even higher efficiencies in terms of their phosphorus reduction. And of course, you can't do a water quality plan without at least considering one detention pond. And here's a couple different varieties. There's a wet pond with a forebay on the left, and the one on the right is actually a variant of a pond. It's called a biofilter. It's intended to have infiltration, but it's served by an underdrain. And all of these things can be very efficient, at phosphorus reduction and sediment reduction, achieving 80% and higher in sediment reduction, which is, around 40 to 60% phosphorus reduction at a fairly affordable cost when you compare it to the life cycle cost of a treatment plant. So we got 220 pounds per year, $220 per pound per year in comparison to treatment plant costs, which is a large number. But when you're looking at making trades for phosphorus, in this case the treatment plants, it's very affordable. All right. So that kind of gets me to the end here, which is good because I'm kind of getting a little bit back on schedule. It all is really about figuring out the impervious area and its connectivity. So you have to do at least some critical assessment of the community you're working in, with the idea then that you're going to build a model or at least crunch some numbers and get some data to develop a hotspot map. Then you target your placement of the BMPs according to what is the land use in that area and what can be done, and of course what's socially acceptable in that area. You don't necessarily want to, build a giant facility that's going to occupy existing development, but if you can, improve your street sweeping or put in some vegetated swales or some other softer practice that's maybe not a substantial change to the way city does business, you can have pretty big improvements. Which takes me to the end. So.
Any questions? We got us back on time almost, too. Any questions here?
Yes, sir.
Could this model be applied to other pollutants like solid waste or nitrogen or?
Well, not so much solid waste in terms of like refuse and trash, but certainly there's a whole host of pollutants that the folks that built the model and did the research, including nitrogen and various heavy metals. I think there is some applications for limited pesticide, but the thing with it is most models function through two mechanisms. The first is through sedimentation. So a lot of the pollutant reduction, the nutrient reduction, is affiliated with particle settling, and the other is through infiltration. And the assumption is if the stormwater with the dissolved pollutants are infiltrated, then it's gone. So there's always the trade-off of, oh, we're putting it in the ground, so therefore it's not surface water's problem anymore. It may eventually become a groundwater issue, but it does do quite a host of other pollutants. Yes.
Do you determine your directly connected impervious, do you do that manually or through GIS?
Almost exclusively through GIS. So I was fortunate enough that I was able to hire a super genius GIS person, and she can write a whole bunch of scripts that will look at what is the dimension aspect ratio of each individual type of impervious. So first of all, you got to classify it by roof and sidewalk and parking and all that kind of business. But then she can take a topographic model, and she can identify what the slope is and the direction of the flow, and then figure out, all right, is it flowing this far, and then is it flowing onto something else? And it's a pretty involved sort of logic train that she went through, but she can do it for a community on an automated basis, provided we've got adequate supporting data. Now, if you're doing a small site, a lot of times, sometimes it's easier just to kind of crunch them the hard way just to get it done, because setting it up takes longer than just doing it. But most of the time when we do a community-wide, we do it automatic.
Time for one more? There is one. All right.
All right.
Good.
Thank you.